Okay, we're going to start doing our lectures and video. Just a couple quick notes about my lectures. I just wanted to kind of point out that down here at the bottom, it actually says that we have, it's copyrighted by Pearson Education. I just used the base of some Pearson PowerPoints that I got. This is not actually copyrighted material. I made the material just to get that copyright out of the way. But the base did start off with Pearson Education, the people that made your book. Anyways, so chapter 2, we'll start talking about motion along a straight line. So we talk acceleration, velocity, etc. So our goals for this chapter are to become comfortable with displacement, how something changes where in its position, velocity, and acceleration. We'll explore some of the motions at constant acceleration. So if you're hitting the brakes and you slow it down constantly, or constantly accelerating in some way. We're going to look at graphs of motion, be able to interpret those, and we'll look at a special case of freely falling bodies or freely falling objects. We call them bodies a lot of times in physics. And we call this special case, we call it free fall. The sections to cover will be sections 2.1 through 2.4. We'll also cover section 2.6 and 2.7 briefly. So motion is divided into two areas of study. We have kinematics, which is going to be our focus in chapter 2. It describes the movement of the object. So it's focused strictly on how something moves. We don't really care about what is causing the motion. Later on, we will care about why the object is moving, and this is the branch that we call dynamics. This is going to be chapter 4, and later we'll talk about dynamics. So we'll build on the things we're learning right now. Displacement is the distance as well as the direction from one place to another, from here to there. Some of the units for it in Standard International, we have it's in meters, and centimeters, grams, and seconds. The distance is centimeters. And the US customary, the base units are feet. Average velocity is defined as the displacement an object undergoes divided by the time it takes to be displaced. So it's the displacement, which is the distance it goes, or the distance and direction it goes, and divided by the time it takes to get there. We'll focus on the total time and the total distance. So we have here a truck driving along, and we talk about its displacement. It started out up here at position at T1 was equal to 6 seconds. So it said when the time was equal to 6 seconds, we started our watches, and then 6 seconds passed, and then at time equal to 6 seconds, the truck was here at position 1. That position 1 we said is x1, which is equal to 277 meters. So it started at some distance. We had some other we had a start line here, which is at a distance of 0, and position x1 is 277 meters from that start position over here. Okay, so position 1, t1 is 6 seconds, or sorry, time 1 is 6 seconds, position 1 is 277 meters. Okay, position 2, some time has passed, the truck is driving towards the start line, and the time is 16 seconds. The position at 16 seconds, x2, position time 2 is 16 seconds, position x2 is going to be 19 meters. It's gotten closer to the start line. So the definition of the average velocity is the change in, since we're talking about just one dimension, we're talking about the change in x. So that's going to be x2, our final position, minus x1, the initial position, divided by the time that lapsed between the two, t2 minus t1. So in order to get delta x, which is delta means change, so delta x is x2 minus x1. This is 277 minus 19 leaves us with negative oops, sorry, this is x2 is 19, x1 is 277, so x2 minus x1 is negative 258 meters. The time it takes is going to be t2, 16 seconds, minus t1, which is 6 seconds. So t2 minus t1 is 10 seconds. So delta x divided by delta t, which is this, leaves us with negative 25.8 meters per second, or we round this to negative 26 meters per second. This can also be written as delta x divided by delta t. We have denoted that the positive direction is to the right of the start line. And so since the truck is moving towards the left, it is moving in the opposite of the positive direction, which would be the negative direction. So that's why we end up with a negative 26 meters per second instead of a positive 26 meters per second. This is dictated by how we set up our coordinate system. If I were to call to the left positive, then the truck would have had a positive displacement or a positive velocity of 26 meters per second. So note this sign convention, the negative goes to the left in this case. So is average velocity a vector quantity? And I'll give you a second, hopefully you think about it. A vector quantity is something that has both a magnitude and direction. Is velocity a vector quantity? Hopefully you say yes. Does velocity have to be constant in order to calculate average velocity? Think about that one for a second. Hopefully you say no. Velocity does not have to be constant in order to calculate its average. I could have something standing still for a minute and then moving. It still has some displacement over some time, so I can still get an average velocity. It doesn't have to be constant. The sign convention, like I was noting a minute ago, it's ultimately up to you, but your typical sign convention is the same as we would just draw a regular Cartesian coordinate system. Typically, we'll have to the right is positive x and upward is positive y. From time to time, when we get into later chapters, we might choose to the left to be positive or down to be positive, but typical sign convention is just like a Cartesian coordinate. If we were to stick with the typical sign convention, where it's positive y is the upward direction, and we're to drop a metal beam off a train trestle. This is actually a train trestle in Washington State at 600 feet above the ground, and it takes 6 seconds to hit the ground. What is the average velocity? Remember that it's our change in position divided by change in time. It's going down to the ground. We'll call the ground at 0. The ground is down here somewhere, and the ground is 0. And it starts out at a positive 600. Our time is delta t is going to be 6 seconds. That's a positive time. Time is always going to be positive. So give the answer too quick there, but we'll have 0. Our position 2 is 0 minus position 1, 600. This will give us negative 600 is our delta y. Delta t, our change in time, is 6 seconds. So we have 600 negative 600 divided by 6 leaves us with negative 100 feet per second. If I were to change the sign convention and label downward as positive y, so instead of having upward as positive y, we have downward as positive y, does that change the velocity at all? Yes, it does. In that case, we would have a positive 100 feet per second. The magnitude is still the same, but the direction is different because we have a different sign convention. How does the average velocity differ from average speed? This little happy face moving around. So it starts out over here at this position, then it comes up and it does a bunch of little stuff over here, and it comes back to here. So we have some time lapse, maybe a couple seconds, and we have some change in position. It started out here, and then it went all the way over here, and then it came back to here. Now, if I were to take time 1 equal to where it's at this point and time 2 at this point, then the position is actually, there's no change in position. It has stayed in the same exact place. So my delta x, or my delta y, however you want to look at it, my change in position is 0. And divided by some time is obviously 0. So my average velocity is 0 in this case. Average speed, however, speed does not have a direction. That's simply how far it moved. Not where it moved to, but how far it moved divided by the time. And so average speed is going to be a positive value because it moved some distance all along here. It's this entire path divided by the time it took to get there. So now let's talk about instantaneous velocity. If the velocity is not constant throughout the path, then it's changing throughout the path, right? Like this. The smiley face is going along. I mean, here it stops for a second, and then it keeps moving along, and then it stops for another second. So how did the velocity change throughout the path? Well, when it was moving down here, it was moving at a constant velocity here. Then the velocity actually changed because the direction changed. And then it changed again because the direction changed again. And then it stopped for a minute. And then it went up over here, down over here, stopped for a minute, and then back. So the velocity was not constant throughout the path. Sometimes we're going to want to know what is the velocity at a particular instant. What is the velocity when it's moving like this? What is its velocity over here? What is its velocity here? What was its velocity when it was stopped? When it stopped, obviously the position isn't changing, so its velocity is 0. So the velocity was changing throughout this, so sometimes it's convenient to talk about the instantaneous velocity. Or sometimes, I shouldn't say it's convenient, but sometimes we need to talk about the instantaneous velocity. Now, what's going on at a particular instant? So a little bit more about instantaneous velocity. The instantaneous velocity can be found with a tangent line to a position versus time graph. We'll go over this in a little bit more detail in a minute. We have to be sure of the sign conventions. Is the instantaneous velocity positive? Is the instantaneous velocity negative? When we get into two-dimensional things, we could have one component positive, one component negative. We also need to know what direction is the motion undergoing. The direction is the fundamental distinction between a scalar and a vector quantity, and we know that velocity is a vector quantity, so we have to be careful about the direction the motion is undergoing. So the definition of the instantaneous velocity, and I realize this is not a calculus-based class, but this has some calculus in it, but your book defines it this way. You're not going to be asked to find limits in this class. But the velocity subscript x, this means the velocity in the x direction, is the limit as the change in time, delta t, goes to 0. So this is the instantaneous velocity right here in the x direction. The x denotes the direction, and it equals the limit as delta t goes to 0, the time goes to 0, of the change in position with time. This is the definition we had from the average velocity. So, but basically what it means is that this is the change at a time interval that's so small that it's like it happens at one particular instance. So t1 and t2 are incredibly close to each other. So instantaneous velocity is this change in position. If you have had calculus, for those of you that are taking this and you have had calculus, you can think of instantaneous velocity as the first derivative of the position function with respect to time. You can ask me about this in class if you want more, or in office hours if you want to know more about it, but it's beyond the scope of this class to define it in terms. Okay, I said that we would talk about instantaneous velocity as being a equal to the slope of a line tangent to a position versus time curve or position versus time plot. So that's exactly what we have here. Over here on the left, we have a dragster that is driving along on this roadway right here. Starts out at some position x1 up here, moves upwards to some position x2. The position x is a function of time. So we say x is equal to x of t, and that's what this blue line is right here. This is the position as a function of time. I have x plotted on the dependent axis, and I have t plotted on the independent axis. So if I want to find the average velocity between 2 points, let's say between this point and this point, we'll call them points A and points B, then I would simply take the distance x2 minus, or the position x2 minus position x1 divided by the time it takes to get there. So time 2 minus time 1. And that would give us this slope, this average slope. That's all we're doing, is we're calculating the slope here, and that is the average velocity. Now, this dragster started out at rest, we can tell, because its velocity is 0 down here, and it's increasing in velocity. So it started out at rest, and it's going faster and faster. So it doesn't really give a very accurate representation. This line right here doesn't give an accurate representation of the velocity down here. It's obviously driving much slower when it starts out and driving much faster once it's going. So instead of calculating the average slope between points A and B, I can move point B closer, call it point B prime, and calculate the average slope again, or calculate the slope so I get the average velocity again. So this is going to be x2 prime minus x1 divided by t2 prime minus t1. This will give us the average velocity, or the slope, between points A and B prime. You can see we're getting a little bit closer to what the real the true instantaneous velocity point A, but it's not quite there because I'm still only averaging between these 2 points. So in order to get the instantaneous velocity, I would need to draw a line tangent to the point at point A, and then I find the slope of that line, and that's the instantaneous velocity. So the instantaneous velocity here is whatever the slope of this line is here, which is less than either of these. It gets over exaggerated by taking a farther away point. So quick little quiz here: is instantaneous velocity a vector? In other words, does instantaneous velocity have both a magnitude, or a speed, as well as a direction? Yes, it does. Can it be positive or negative? Can I set it up so that instantaneously it can be moving in the positive x direction, or in the negative x direction? Yes, I can. Is it possible to have a positive position and a negative velocity? Or how about a negative position and a positive velocity? Is it possible to have those two? Think about those for a second here. Can it be located somewhere in the positive x, but so this positive position means it's located maybe somewhere in the positive, it's to the right of some line, which is to the right of some starting point, and a negative velocity. If it has a negative velocity, it would just simply mean it's moving to the left. So yes, that is true. How about a negative position and a positive velocity? Well, if it can have a positive position and negative velocity, it can also have a negative position. It can be located in the negative range and have a positive velocity. So both of these are true. From here on out, velocity is going to be referred to as the instantaneous velocity. So if I say velocity, I mean instantaneous velocity. I'll explicitly say average. Okay, so just a little bit of a graphical representation of what we were talking about in the previous slide. We have here a graph of an object moving. So this blue line right here is the path of the object, and it's a function of the object's displacement with time. So we have over here on the dependent axis is the displacement x, so negative or positive, and then we have the time located on the independent axis. And so at point A, or time A, it starts out and the position is negative, right? We have here negative position, obviously below the origin here, so the position is negative. And then since the velocity is the slope of the line tangent, the instantaneous velocity is the slope of a tangent line, then we look at the slope of the line that comes through here. We draw a tangent line, that's this green line here. And the slope of that is positive, right? So the velocity is positive, and it makes sense because, you know, it's moving in the positive direction. So we have a negative position, yet a positive velocity. And if we were to come over here and plot it just on a kind of a straight line here, we have the time at t equal to a, and that's, we set that equal to time 0. And the velocity is positive, so we'll draw it to the right, and the position is negative, so we draw it to the left of 0, and we put a vector, an arrow to the right, showing that the velocity is positive. If we come over here at time b, the position is located at 0, right? It's located right on the axis, so the position is at 0, and the slope here, when we draw a tangent line, well, it's a very almost a vertical line, right? So it's a very large slope. So we come over here at time b, the position is at 0, and you'll notice that the line here is much longer, and the vector here is much longer than the vector here, because the velocity is much greater at time b than it is time a. That's because the slope is much greater when it runs through b than it is when it goes through a. Again, we'll do the same thing at time c. What's the position at time c? Well, the position here would be positive, right? It's located above the origin, so the position is positive. And the slope of a line tangent to this would be, it's a horizontal line, right? So the slope is 0, so the velocity is 0. So the object has come to a momentary stop right here. And then it starts moving down like this. The position here is still positive, and the slope here is negative, right? So that means the position is positive while the velocity is negative. So position is positive at time d, position is positive, and the velocity is negative, so now it is moving to the left, right? So it's located to the right of 0, but it's moving to the left. And then at time e, it's still positive, still has a positive position, and it still has a negative slope, so it has a negative velocity, but this is much less than this, right? So the velocity e is much less than the velocity at d. So we see here at time e, the velocity, our position is positive, and velocity is a very small negative velocity. Okay, now let's talk. So average acceleration, virtually the same definition as the average velocity, is the change in velocity vectors v2 minus v1 divided by the time it takes for that change, so t2 minus t1, also written as delta v over delta t. Instantaneous acceleration, same definition as the instantaneous velocity, it's just the limit as this delta t goes to 0. So as the time interval gets smaller and smaller until it's virtually 0, defines our instantaneous. Slide right here, does it have a direction? Can it be positive or negative? Does it have a direction that goes with the acceleration? If it's talking about a change in velocity with time, and if velocity has a position as well as a magnitude with it, then acceleration must also. So if a changing position and time again. So acceleration is a vector quantity. Can acceleration be positive or negative? Of course, it just depends on the sign convention. Can velocity be positive and acceleration negative? I kind of hinted at this a minute ago. Of course we can. We can be moving in a positive direction, but slowing down. That's when we'd have negative acceleration. Or we could have vice versa. We could be moving in the negative direction. I could be traveling to my left, but slowing down, so I'm traveling less quickly in the left direction. So that would be an acceleration to the right. It would be a positive acceleration. Sorry. I'll have some small negative minus some larger negative. I'll end up with a positive value. So I'll end up with a positive acceleration. You can see that the change in vectors between here and here, this one minus this one, is that direction, right? It's going less negative, so the acceleration will be positive. So a quick note on the average and instantaneous accelerations. Note that we still have sign convention still prescribes whether or not the sign of the acceleration is positive or negative. If I flip the sign convention around, then it changes the positive or negative. It simply just depends on how we set it up. If the particle velocity of a particle is changing, period. If velocity is changing, then the object must be doing what? Think about it for a second. If the velocity is changing, then by definition we have a change in velocity divided by some time interval is acceleration. So if the velocity of a particle is changing, object must be accelerating. What are some of the ways, what are 3 ways that a car can accelerate? Think about it for a second. You step on the gas, you speed up. Opposite of speeding up, we could step on the brakes and slow down. But how else can we change velocity? We can also change direction. So we can speed up, we can slow down, or we can just turn the steering wheel and turn the car so that the direction changes as well. So the direction where velocity changes means it's accelerating. So if I go around a curve, I'm accelerating, even if I go at constant. Okay, let's have a little pop quiz on average and instantaneous acceleration now. If you have 2 cars passing each other in opposite directions in the freeway, so maybe one's going north, one's going south, one of them is speeding up at 10 miles per hour. Say the north one is, the one going north is speeding up at 10 miles per hour every hour. And the other one is slowing down or decelerating at 10 miles per hour. How do their accelerations compare? So essentially, let's say we have one that starts out here and it is heading north like this, and it's accelerating. So it starts here and it starts out slow and it speeds up, right? It's accelerating, and it's accelerating in this direction, up the screen. I have another car that's traveling south like this, and it's decelerating. So it means that it's traveling south, and then it was traveling fast at first, and then it slows down. So it travels fast here, and then it slows down like this, right? So which direction is that accelerating? Well, if it's traveling this direction and slowing down, then it's also accelerating up the screen north to the north direction. So this one was accelerating this direction, and this one over here is also accelerating this direction. And their magnitudes are the same, 10 miles per hour, so their accelerations are exactly the same. Conceptual analysis 2.3 from page 41. Let's run over this one. So this figure shows a graph of velocity versus time for a moving object. The object moves on an east to west axis, with the west chosen as the positive direction. So west would be positive. So this is the velocity, this is the time. The positive direction says west is chosen as the positive direction. So this direction would be west, and then this direction would be east. Because if west is positive, east would be negative, right? So which description matches the graph? The object speeds up continuously while moving westward. If it's speeding up continuously, then we would have to say that the velocity would be continuously increasing, right? If the object speeds up continuously, velocity is continuously increasing. So this looks pretty good to have a continuously increasing velocity, but it says while moving westward. So it would have to be moving westward the entire time. So it would need to be in this first quadrant. It would need to be in this region up here to be continuously moving westward. So that one's not quite so good. What is it actually doing here? It starts out east, right? It starts out moving east, and it's moving with a pretty significant eastward velocity, right? It's very negative, or it's very east, a large eastward velocity. Then the magnitude of the eastward velocity decreases, right? It's going less east because it's less negative, and less east again because it's less negative here, until it finally reaches 0. So it's not moving at all, actually. And then its velocity becomes positive. It becomes westward, right? As we move here, and it becomes higher and higher velocity in the westward direction. So what starts out east, it seems to slow down in the east direction until it finally comes to a stop. And then it reverses and goes to the westward direction and increases in the westward direction. So the answer would actually be D. The object moves east while slowing to a stop, then moves west while speeding up. Can we tell anything about acceleration from this graph? Well, we know that acceleration is the slope of the velocity versus time plot. This is a velocity versus time plot. And we know this is the slope. And the slope here, let's just take this region right here. The slope here is some positive value. It looks positive 1 maybe. The slope here is also about a positive 1 and positive 1 here. The slope is constant. It's a straight line, so the slope is constant. So if the slope is constant and the slope of the velocity versus time plot is acceleration, then we can say the acceleration of this object is constant. Okay, so in real life, we might ask some questions about if we're driving in a car, we're about to hit a tree, we might think to ourselves, can I actually stop before I hit this tree? We also might, in the same situation, maybe we're out running a police motorcycle, and we might ask the question, when will the police motorcycle overtake a speeding car? Maybe it's our car, maybe it's somebody else's. So we have physical equations, equations of kinematics or equations of motion to answer these types of questions. We have several relationships and several equations that are associated with these relationships. If we have a relationship between velocity and time here, we have a corresponding equation. Vx is equal to v naught x plus axt. Or the velocity in the x direction is equal to the velocity at time equal to 0. That's what that 0 represents. It's velocity at time equals 0 as our starting velocity in the x direction plus the acceleration in the x direction times time, how long it was accelerating. Similarly, if we have a relationship between displacement and time, x is our displacement, it's our linear displacement here, and this is equal to x naught, or x, our position at time equal to 0. We say x naught, or our starting position, initial position here, plus the velocity, our starting velocity in the x direction, v naught x, times the time, how fast it was going times how long it was going, plus 1/2 of the acceleration in the x direction, 1/2 ax, times the time squared. So x is equal to x naught plus v naught xt plus 1/2 axt squared. We also have a relationship between velocity and displacement. The velocity in the x direction squared is equal to the initial velocity, or v naught x, the initial velocity in the x direction squared, plus 2 times the acceleration in the x direction times delta x, our position minus our starting position. X minus x naught is just delta x, or how far it traveled. So this relates the final velocity, or some velocity in x at some given time, is equal, and that squared is equal to our starting velocity squared plus 2 times the acceleration times the distance it traveled. Okay, so let's run through a quick example using some of those equations. We're given here a motorcycle. Starts out at x naught, or the time equal to 0. X naught is equal to 5 meters. V naught x, so the starting velocity in the x direction, is 15 meters per second. The acceleration in the x direction is constant, so I don't need to put a subscript for the time because it's constant everywhere. A naught x is equal to a1x is equal to a2x is equal to a3x. So we'll just say ax, it's constant acceleration, and that's equal to 4 meters per second squared. So using the equations that were on the previous slide, we can find out what x is when the time is equal to 2 seconds, and we can also find out what velocity at point x is. So what is the position and the velocity of the motorcyclist at time t equal 2 seconds? You can pause the video and you work this out. Maybe rewind the video a little bit, look at those equations, or look in your book, or maybe you have them written down. But work those equations, and give you a second here. Position and velocity. The position will be x is equal to 43 meters. So this distance right here, it has traveled 43 meters, and the velocity is equal to 23 meters per second. Where is the motorcyclist when his velocity is 25 meters per second? So we can change these equations around quite a bit, and that's something that we have to get used to with physics, is that there's a lot of variables in these equations, and we can be given one thing and solve for many others. So we can also find out, if we knew the velocity is 25 meters per second, where is he and how long does it take him to get there? We can solve for both the position as well as the time using a couple of those equations together. So try to do that now. And we'll work through several of these in class, but try to do this now. And hopefully you got x is equal to 55 meters, and the time would be 2.5 seconds. And you can plug it in to verify, plug it into velocity is equal to v naught x plus axt. The velocity is 25 meters per second. If we plug in the acceleration times the time and the initial velocity, then we should get we should verify that it'll be 25 meters per second. Okay, in this slide we're showing sort of a graphical representation of these equations. So this equation, x is equal to x naught plus v naught xt plus 1 half axt squared. So you can kind of see where these come from, just for a more complete understanding of these equations in motion. So we start out at x naught. So the position, obviously this is x at some given time t. We start out at x naught. That makes sense. We start out at some starting position. Now if we were to travel along at constant velocity, we would travel along at this path right here. And we would say at some time t, our position would be x naught, where we started, plus velocity in the x direction times the time. And that would give us up to right here. And then if we're accelerating, we're increasing the velocity constantly. So that's where we get this arc part from right here. So the effect of the acceleration is to put this curve in here. And so we actually would increase even more, a magnitude of 1 half axt squared, which would put our position right here. So essentially this is our starting position. This is what we would get if we have zero acceleration or a constant velocity. And that's important to know that that zero acceleration means constant velocity. And then this is the effect of the acceleration right here. Bumps it up a little bit more. Obviously, if we're speeding up, he's going to be traveling farther and farther, faster and faster. If we change this around, here we had position versus time, here we have velocity versus time. So this graph shows a graphical representation of the equation Vx is equal to V naught x plus axt. Velocity is equal to starting velocity plus acceleration times time, which again, we start out the same way. It makes sense that our velocity at some point in time would be our starting velocity plus the acceleration times the time. Right? So our starting velocity is here, and then we're accelerating and we're increasing our velocity, and we come over to some time t over here, and we would move up to get this is our new velocity with the acceleration here. So it's a starting velocity plus the increase due to the acceleration here. Now we'll move on to section 2.6, talking about freely falling objects, or freely falling bodies, sometimes we'll call them in physics. So which of these would fall faster, a basketball or a feather? And you might say that it would fall at the same rate, but you'd probably have taken physics before if you said that. And usually you'd say if we're dropping them on Earth, you would say that basketball would fall faster, right? But what if we take air resistance out of the picture? The reason that basketball actually falls faster is because the feather has the effect of air resistance slows it down more because it's lighter. So there's a frictional resistance, which we'll talk about much later. But if we just take air resistance out of the picture and we put it in a vacuum is a space that's void of any air whatsoever, so that we wouldn't have any air resistance, then we would actually get the basketball and feather falling at exactly the same rate. So in order to understand kind of the basic principles behind physics, we'll first consider no air resistance. So we call that free fall. So free fall is this idealized circumstance in which we have no air resistance. And the assumptions we make in free fall are that all objects fall at the same constant rate if we neglect air resistance, proximity to Earth, or rotation of the Earth. Air resistance slows down the object due to friction. You can try dropping a piece of paper or a pencil. The paper will fall slower because there's a larger surface area and there's more resistance. The proximity to Earth, we'll get into this in chapter 6, but how close the object or the objects are to Earth actually affects how quickly they accelerate towards Earth, and the rotation of the Earth also comes into effect. But free fall is an idealized circumstance in which we neglect all of these, so that the takeaway from this is that in free fall, all objects will fall at the same constant rate. And we'll be making this assumption all throughout chapters 2 and 3. A couple constants we have here. The acceleration due to gravity is equal to 9.8 meters per second, or 9.8 meters per second squared. This is acceleration due to gravity on Earth. It's different on different planets. But it's 9.8 meters per second squared, and this is in SI units, standard international units. And US customary units, it's 32.2 feet per second squared. This is assumed to be constant. There's actually some slight variations even on the Earth, but not enough to really worry about. So we'll assume this to be constant, both of these quantities to be constant. So this is just a little bit of a background on kind of how the ideas of free fall developed. As the story goes, Galileo dropped objects from the Leaning Tower of Pisa. One was heavy, one was light. They hit simultaneously, which disproved Aristotle's assertion that heavy objects fall faster. Aristotle had previously said that, oh, heavy objects have to fall faster. This was proven further when a feather and a hammer fell on the moon during Apollo 15 mission by astronaut Dave Scott, and they actually fell at the same time. They hit at the same time, so they fell at the exactly same rate. So the key is that Galileo was right in the absence of air resistance. So sort of just another way of saying what I said on the previous slide. If we have no air resistance, or we have no air, then everything falls at. So maybe a little bit more kind of up-to-date way to look at this, instead of dropping things from the Leaning Tower of Pisa, is that we have an apple and a feather that are dropped from this hole in the sky, hole in the ceiling here, and they're dropping in a vacuum, so there's no air in here, and obviously no air resistance if there's no air. And the picture is taken with a strobe light so that we can take 4 images very quickly while it falls. You can see that they fall at exactly the same rate. The apple's not actually falling any faster than the feather. So the takeaway from this is that if we were to neglect the 3 things that are previously stated, the air resistance, proximity to Earth, and the Earth's rotation, we can use all the equations of motion that we used previously for the motorcycle example. We can use all those same equations to solve problems of free fall, of things falling off of objects. So we'll make this assumption a lot so that we can use those same equations to solve. And the last thing I want to touch base on in this chapter before I just put up some example problems for you, is relative velocity. And this is relative velocity moving in a straight line. This is all linear motion in chapter 2. So say we have a train. We have a bicyclist just kind of sitting here watching his clock, timing things, right, getting the velocity. And he's watching this train move, and this woman is inside the train, and she's walking forward along the train. Okay, so pretend that you're the woman in the train. When you look around you, if you're standing still, you look around you, it looks like nothing is moving. If you're looking inside the train, not looking out of the window, it looks like nothing is moving. If you start walking forward, then it looks like you're moving, or maybe the things behind you are moving. Or that things are moving behind you. So to her, the train is stationary and she is moving in the train. Now to the cyclist is sitting outside the train and he sees the train moving, and if he can see the woman through the windows, then he would say, well, the woman's moving even faster than the train. Right? Because the woman, well, she feels that she's moving faster than the train, and the cyclist says, well, the train's moving and the woman is moving faster. So this is what we mean by relative velocity. To the woman, she's moving just regular pace. To the cyclist, she's moving 100 miles an hour, or how fast the train is moving, plus her regular pace. So a way to think of this graphically in terms of charts, we have the frame of reference of the cyclist starts here. So his frame of reference, I should say, is the Earth, right? So everything is sort of just stationary on the Earth, and the train and the woman are both moving. So that's his frame of reference. The woman's frame of reference is this one right here. The train's frame of reference, I should say, is everything inside the train is not moving. So the train itself is kind of like the Earth. The cyclist sees everything on the Earth is not moving. Anything inside the train, it seems to be not moving relative to the train, right? The woman, this is the position of the woman with respect to the train. And the woman feels like she is moving forward with respect to the train. Now, the position of the train with respect to the cyclist, well, the cyclist sees the train moving forward as well, right? So the position of the train with respect to the cyclist is that it's moving forward, and the position of the woman with respect to the train is that it's moving forward as well. Now, if I were to add these two together, then I would get the position of the woman with respect to the cyclist, because the train looks like it's moving forward to the cyclist, and the woman looks like she's moving forward with respect to the train. Add these together, and it looks like the woman is moving very fast with respect to the cyclist. And that's pretty much a brief summary of the relative velocity along a straight line, which we'll do a little bit more in class, but I'm not going to go into a ton of detail on this topic. So some example problems that I wanted to throw up here just for you guys to do before we get into class and kind of try these. And I have the solutions kind of written out a little bit, but try to do these problems. So suppose actually I won't read it. You guys can read this and you guys can work on this on your own. So maybe pause it, read it, and we'll work on it together. Okay, after we've read the problem, we need to find a way to decipher this. This is a typical physics problem. It's a long paragraph with many things defined and many things given. So we need to develop a way to organize our thoughts. One of the best things to do is to label what's given, what are we trying to find, and what are the assumptions that we need to make in order to solve this problem. Now, we were given that there was an initial velocity in the y direction of 15 meters per second. We're also given that the initial velocity in the x direction was 0 meters per second. And the things we need to find, the question asked us for, was the position and velocity at a time equal to 1 second and 4 seconds. So it's sort of some more of the given in there. We're looking for the velocity when the ball is 5 meters above the railing. Again, we're given something here. We're given a position, and we're looking for the maximum height at which it occurs. Oh, maximum height and time at which it occurs. Some of the assumptions we need to make is that there's negligible air resistance, or there's no air resistance whatsoever. That way we can use the equations of motion that we used on the motorcycle example. We also need to assume that the acceleration in the y direction is a constant negative 9.8 meters per second squared. Now the reason it's negative here is because I'm sticking with typical sign convention that says that we have a positive y is upwards and a positive x is to the right. Now acceleration is always down, or gravity always accelerates down, right? So if I call positive upwards, then acceleration must be negative. So we'll typically use acceleration due to gravity as negative 9.8 meters per second squared, because our sign convention will typically make it negative. Doesn't have to be. If you choose to use a different sign convention, it can be different, but I wouldn't recommend that. So when we start this, we're going to place the origin at the top of the roof with time equals 0 being the time the ball leaves our hand. So origin will be at the top of the roof. And we'll go through and we'll solve this. So we'll solve this in class, but hopefully you've tried it on your own. And these are the answers to this particular question. Do the next problem. This is problem 2.59, and we have the same sort of scenario. So take a minute, pause this, try to work it out, and see where you get, and we'll go over this in class. But please try it. Come into class with questions. It's the only way you're going to be able to learn this stuff. So again, we let F denote faster stone and S denote the slower stone. We're going to have a ton of subscripts in this class. So we have to get used to using those to help to organize our many word problems into sort of mathematical form. So V naught F is the velocity at time equal to 0 of the faster stone. So, or the starting velocity of the faster stone, V naught F. And this is equal to 3 V naught S. So this just says that the velocity of the faster stone, the starting velocity of the faster stone, is equal to 3 times the starting velocity of the slower stone. The time of the faster stone is equal to 10 seconds, and this is to return to the ground. This is all the way up and then all the way back down, right? The maximum height of the slower stone is equal to h. So this is what's given to us. The velocity of the faster is 3 times the velocity of the slower, the starting velocities. The time that the faster one travels is 10 seconds, and the maximum height of the slower one is equal to h. The things that we're trying to find, and well, you want to use the same subscripts, the same notation that we used and we were writing out what was given to us, is the time for the slower stone to return to the ground is TS. This is what we're looking for. We're also looking for the maximum height of the faster stone, or Y max F. And we want this in terms of h, because Y max S was given in terms of h, we'll need to give Y max F in terms of h. Again, it's important to note the assumptions that we have to make in order to make this true. So, free fall conditions. Wrote this one a little bit differently than the last one, because free fall conditions encompasses several things. Acceleration in the y direction is a constant negative 9.8 meters per second squared. This is just the acceleration due to gravity on Earth. And we assume all the free fall conditions, air resistance, proximity to Earth, and Earth's rotation are all negligible, so that we can use the equations that we had before. We have to make these assumptions in order to be able to use those equations of motion that we used in the previous problems. You work through the solution, and hopefully you guys get this, but again, if not, we will be covering these in class and additional questions.